Physics is fun. For the next topic, 6.2, we will look at electric fields. State that there are two types of electric charge. Okay, that's easy. There are two types of electric charge, positive charge and negative charge. Like charges repel, unlike charges attract, which means if they're like, positive and positive, they repel. If they're unlike, positive and negative, they attract. The unit of charge is called the Coulomb, and it can have a positive or a negative value. For example, the charge on an electron is 1.6 times 10 to the minus 19 coulombs. This is a very small charge, but electrons are very small. State and apply the law of conservation of charge. The total charge before an interaction is equal to the total charge afterwards. For example, two metal spheres are charged with plus 5 coulombs and negative 3 coulombs, and they touch each other. Then the charge is evenly distributed between them. What will the charge on each be? So we have plus 5 and negative 3. We add them together, we have a net charge, a sum of charge of 2 coulombs. When this is distributed between two spheres, this 2 coulombs basically gives 1 coulomb, so this is how much charge will be on each sphere. Describe and explain the differences in the electrical properties of conductors and insulators. Conductors, for example metals, they allow electricity to pass because there is a sea of electrons between the atoms, and they're able to transfer the charge. By the way, this says free atoms. This is not true. The atoms are not free, the electrons are free. Insulators, or non-metals, for example, they do not allow electricity to pass through. The electrons are bound to the atoms and not able to move away and transfer the charge. A solution, such as an ionic solution, this is a conductor because it has free moving charged particles, anions and cations, which are able to flow through the solution and transfer charge. So if charge is able to be transferred, whether it be positive charge or negative charge, then it will be able to conduct. State Coulomb's law. Force between two charges, Q1 and Q2, is A, proportional to the product of the charges, in other words Q1 times by Q2, and is B, inversely proportional to the square of the distance between them. And this can be represented by the equation F equals K QQ over R squared. Notice we have Q times by Q, the product, and we're dividing by R squared, so it's an inverse relationship with the square of the distance between them. The Coulomb constant K has a value of roughly 9 times 10 to the 9 newtons meter squared per coulomb squared. K can also be represented by 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space, and this gives a value of how well or how poorly space or the medium is able to conduct the electric field. So this is the equation. This is the main one. F is equal to KQQ over R squared, Coulomb's law. And it's very similar to the law of gravitation. Remember, F is equal to GMM over R squared. Define electric field strength. Remember, the gravitational field strength is the force per unit mass. However, the electric field strength is the force per unit, not mass, but per unit charge. What are the units? It's going to be force is newtons per unit charge is 4 newtons per coulomb in the direction that is felt by a positive charge. and positive is repelled by positive and goes towards a negative charge. So this is the equation for Coulomb's law. F is equal to kq over r squared. And we're interested in the force per unit charge, so we divide by charge. Q1s cancel, and we have E is equal to kq over r squared. Compare with G, small g, is equal to gm over r squared. There are parallels here. Electric field strength. So the electric force per unit charge, which is felt by a small positive test charge. Why does it need to be a small positive test charge? And we will look at that now. So this is electric field strength. If we have a test charge in an electric field which is caused by this large charge, there's a distance between them, the electric field strength by this small charge will be kq over r squared, where q is the charge on the large charge. This is a small test charge. So what happens here is there will be a force acting away on that small charge. So the electric field will be away from the large charge. So the small test charge will move away. What happens if this charge is very large, if we try with a large charge? So we'll make a much larger charge. Now this small charge would now become larger, will actually cause its own electric field, and the bigger it is, the more it will disturb the electric field that it is in. In fact, you can imagine what will happen is that this large charge here, the negative charge will be pulled to the left towards this charge, and the positive charge will be pulled away. So this already disturbs the electric field which is produced by this. Now, effectively, since we have negative charge here, there's going to be a weakened force, because this will be attracted to this force, not repelled. So remember, you must talk about a small positive test charge. It has to be positive because that determines the direction, and has to be small, otherwise it will start to disturb the electric field in which you put it. You have to draw the electric field patterns for different charge. First point is that where the lines are close together, we have a strong electric field. When the lines are far apart, we have a weak electric field. So basically, the electric field weakens with distance. The further away you go, the weaker the field gets. And we know that because we know that the electric field strength varies with r squared. It falls off very rapidly with distance. Next point, we need to draw the electric field patterns for different charge configurations. The first field, the lines point towards the charge, so this charge must be negative. Remember that all positive test charge moves towards the negative charge, so this must be negative. In the second field, the lines point towards the charge on the right, so that must be negative, and away from the charge on the left must be positive. The third field, the lines are always pointing towards where the charges are, so they must be negative charges. Note that there's a point between the two charges, between the two like charges, where the electric field lines basically cancel out, and this is what you have is called a neutral spot. And the fourth here, which I haven't managed to draw, will look very similar to the one above, but they're exactly the same shape, but the lines will be pointing in the opposite direction because they would be pointing away from the positive charges. Now we need to draw the electric field pattern between two parallel plates. The field lines are parallel and equidistant between the plates. Notice the distance between them is the same and they're parallel. And what this means is that the field is uniform. And another thing to note is that the field lines go from positive to negative, because that's the direction felt by a small test positive charge. At the edges of the plates, however, the lines curve out, and it means that the field is weaker there. Here we have another couple of diagrams showing the direction of the field lines between a positive charge and a negative charge, and the same thing here, the same thing here. Notice there's a neutral point here, and this one is not so easy to see. You can't see the direction, but you notice well that the lines are parallel here and close together, and towards the edge they curve away and they get further apart, which means the field is weaker here.